SwayamPrabha. Digital India. Educated India.
Welcome back. So we were discussing the second law of thermodynamics, and until now we have looked into the fact that any process to occur should satisfy the first law and the second law. And we also discussed about a particular statement called Kelvin-Planck statement. It states that it's impossible to have a device which works on a cycle and it just takes energy from a single thermal reservoir and produces a net amount of work. So that is impossible to have. So we will discuss in this particular lecture refrigerators, heat pumps, and I describe an equivalent statement of second law of thermodynamics, as we have discussed already the Kelvin-Planck statement. In this lecture we are going to describe Clausius statement of second law of thermodynamics. Okay, and later we will show that Kelvin-Planck statement and Clausius statement are equivalent. Okay, so let me start with the refrigerator. Now, as we know that heat transfer from a high temperature to a low temperature, thus in order to transfer heat from a low temperature to a high temperature, it cannot be done automatically, and what we need is a special device. This special device is a refrigerator. Okay, and the refrigerator basically maintains space, refrigerator space, at a specific low temperature by removing heat from it. It works on a cyclic device and it has a working fluid which we call refrigerants. Most frequent refrigeration cycle is a vapor compression refrigeration cycle, which consists of compressor, condenser, expansion valve, evaporator. This is just illustration here. So you have your compressor, your condenser, expansion valve, evaporator, the refrigerant which enters compressor as vapor. So this is here as vapor. Okay, it's compressed. The outlet of the compressor contains a compressed refrigerant at a pressure which is the condenser pressure. So this pressure is much higher than this. Okay, and here the condenser rejects heat to the surrounding. So this particular condenser is typically the coils at the back of your household refrigerator. Okay, so it rejects heat to the surrounding medium, which is basically the kitchen air. So here this is a vapor, and then this condenses to a saturated liquid here. Okay, so this is your saturated liquid. It gets expanded, so it lowers its pressure, and then from here at this evaporator, it takes heat from the refrigerator space and evaporates to a vapor state. Okay, from this particular state, which is a liquid, to the vapor state. So this is the overall cycle, and this is a cyclic device. Now let us look at how you define efficiency. You recall that heat engines, when we described, where in order to convert the heat to work, we needed a device called heat engine. We defined thermal efficiency. Okay, and here we are going to describe the efficiency of refrigerator as coefficient of performance. Okay, so this is to discriminate from heat engine efficiency, and you will see very clearly why. The definition as far as the efficiency is concerned is the same, where that efficiency is nothing but the ratio of the desired output and required input. Okay, but the objective of the refrigerator is different from that of heat engine. Here the objective is to remove heat from the cold refrigerator space, which is at a specific temperature TL. Okay, so essentially what is the desired output? Desired output is a QL, and work is needed in order to remove this, that means transfer the heat from a TL low temperature to a high temperature, okay, warm temperature. So the required input is your W net in. So that would be the coefficient of performance for R. That would be the efficiency as far as the refrigerator is concerned. Now, if you can apply a conservation of energy principle and write W net in as simply as a difference of QH minus QL. Okay, thus you can write your coefficient of performance simply as QL divided by QH minus QL, or in this form. So the question is, can the value of coefficient of performance for a refrigerator be greater than unity? And the answer is yes. that can be if the amount of heat extracted or removed from the cold space is more than work input work required in order to achieve this transfer of heat from the TL to high temperature. So yes, the answer is that the COPR can be greater than unity if your QL is greater than W net in. Okay, so in a similar philosophy you have heat pumps where the process is almost similar. However, the desired output is different from that of a refrigerator. The desired output is the heat transfer to a specific space, which is basically your room. For example, you want to heat it, and so you want to keep that particular room temperature at a specific temperature. So that will be your heat pump. So this is another device that transfer from a low temperature medium to high temperature medium, but the objective is different from that of a refrigerator, and it is to maintain a heat temperature. So this is the space which you want to maintain at TH, okay, by supplying heat. So the supplying heat becomes the desired output. Okay, so overall the schematic is almost similar to what the refrigerator we have used, except the fact that the desired output is different from that of refrigerator. For the case of refrigerator, the desired output is of that of QL. So COP, the coefficient of performance for heat pumps, again we will write it in this form: the desired output divided by required input. Okay, but the desired output is not anymore QL, it's QH. Okay, and the required input is still W net in. So you can rewrite in this form. You can use your first law of thermodynamics and describe W net in here. Okay, is nothing but QH minus QL. Okay, and that's what you're going to write here, and then you can rewrite in this form. Okay, so this is a simple illustration of a heat pump. You have a house which you want to keep at a temperature 20 degrees C inside, and in order to do that you need to supply heat at 7 kilojoules, and the outside temperature is 4 degrees Celsius. So in order to achieve this, if you apply W net 2 kilojoules and the QL is 5 kilojoules, then the COP would be simply QH divided by W net, which is nothing but 7 by 2, and that is turns out to be 3.5. So the question is, can the value of COP be lower than unity? And this is possible if you have a lot of heat losses through pipes and other devices which is part of this heat pump. So in practice it can be possible. Okay, note that the air conditioners are the basic refrigerator. Okay, so where the room becomes the refrigerator space. So in the refrigerator, the freezer becomes, for example, the refrigerator space. For the case of air conditioner, the room itself becomes a refrigerator space. Now if you turn AC around backward and install such that the refrigerator space is outside, then it can act like a heat pump. So air conditioner, if installed backward, can act like a heat pump. Okay, so let me talk about the silent features of refrigerator and heat pumps. Most heat pumps in today's operations have a typical COP of 2 to 3. Okay, most existing heat pumps use the cold outside air as the heat source in winter. The efficiency of a heat pump drops considerably when the temperature are below the freezing point. In such case, you can make use of geothermal heat pump where the ground becomes as a heat source for such geothermal heat pumps. It's more expensive to install geothermal heat pumps, but it's more efficient. The air conditioners are basically refrigerators whose refrigerator space is a room or building, as I already mentioned, instead of the food compartment. Okay, COP of a refrigerator decreases with decreasing refrigeration temperature, which essentially means that it is not economical if you reduce the amount of temperature or the temperature you want to keep it for the refrigeration. So thus refrigerating to a lower temperature is not sensible at all. Okay, let me revisit the second law of thermodynamics. We already talked about Kelvin-Planck statement of second law of thermodynamics, which is that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produces a net amount of work. So now we will discuss the Clausius statement for the second law of thermodynamics. It says that it is impossible to construct a device that operates on a cycle and produces no effect other than transfer of heat from a low temperature body to a high temperature body. Now in both the cases it says that you have 100% efficiency. So it tells you that 100% efficiency is not possible. So let me first discuss a bit more of clause statement, and then we'll talk about the equivalence of both the statement. So clause statement tells you that device such as this is not feasible, okay, because it says that you have no effect other than transferring this heat to a warmer environment completely, okay, which means there is no work input, okay. So this is not possible as far as the clause statement is concerned. This refrigerator violates the clause statement of the second law. So in other words, you need an external work to transfer heat from a low temperature to a high temperature, and as of now the second law based on experiments, and till date it has not been violated. Okay, so let me discuss the equivalence of the two statements. Both the statements are equivalent, okay. So which means any device which violates Kelvin Planck statement will also violate clause statement, and vice versa. So let's consider a refrigerator that is powered by a 100% efficient heat engine. So which essentially means that your heat engine violates, or this fictitious heat engine violates second law of thermodynamics, but let us assume that such a heat engine exists. So which essentially means that you have heat engine which converts heat to completely to work, and this work is an input to the refrigerator which transfer heat from the low temperature to the high temperature. So this is now the overall device. So we can consider this collectively, we can put this together, and then since QH is same as QH, this will cancel out. So effectively one can describe this device in this form, okay. Now what it means here is that there is no external work required to transfer heat from a low temperature reservoir to a high temperature reservoir, and this is the equivalent refrigerator, and this particular refrigerator violates the clause statement, okay, and thus it tells you that if one particular statement is violated, the other statement would get violated as well, and vice versa. Okay, so that would be the end of this particular lecture. So in the next lecture we are going to describe the perpetual motion and reversible and irreversible processes. So I'll see you in the next lecture.